Alrighty, folks, so we are back for section 2.4, which, as I mentioned a lot last time, is all about continuity, right? So in both math and English, continuity basically can be summed up as something that doesn't have any breaks, right? No jumps, no leaps, nothing that sort of breaks the flow of something, right? So math, we specifically mean when we're talking about no breaks, and by the way, I mean breaks like this, not breaks like your car has, right? We specifically mean functions that we can draw on the paper without lifting our pen. Right, so this is an example. At least my drawing didn't, sort of skipped a little bit, but there we go. This is an example of a line with no breaks in it. I could do it in one solid, smooth motion. And that's graphically what it means to be continuous, right? Our definition is that the limit as x goes to c of f of x equals f of c. And if you're eagle-eyed and really comfortable with your function notation, you'll note that, in other words, this means that the substitution that we talked about last time, that we said we could do for power functions and sums and quotients of power functions, we said we could substitute and use that as a way of finding the limit. Well, really, the definition of continuous is that you can do it for that function. A function is continuous if you can, if this limit equals what you get when you actually plug in that number to the function. Right? So there's three sorts of things that have to be true then. One, f of c has to exist. Right? That's a pretty important one. You can't be equal to f of c if there's no such thing as f of c. Two, the limit as x goes to c of f of x exists. Right? Obviously, you can't be equal to the limit as x goes to c of f of x if that doesn't exist. And three, of course, the definition is that they are equal. Right? And we split it up in this way because why something fails to be continuous can be very important. Right? So, a quick example. This would be something that breaks 1. Right? So where c equals 0, f of 0 doesn't exist, but that limit does. But the limit can't be equal to f of 0 because there's no such thing as f of 0. Right? So again, with c being 0, this doesn't work because that limit doesn't exist. Right? We talked about things like this when we first talked about doing limits graphically. Right? The limit from the left and the right exist, but they're not equal to one another, so the limit doesn't exist. And this last one, I'm actually going to take that first one and change it just a little bit. Again, c equals 0, and we fail this one because the limit exists. It's up here, right? We'll call that 2, right? And the function exists. It's down there. We'll call that -1, but they're not equal to one another, right? So those are ways you can break each of those. And specifically, I wanna highlight something from 2 real quick, right? Which is that if limit x goes to c of f of x does not exist, but limit as x goes to c from the left of f of x equals f of c, I'm going to be lazy. Make use of my software. There we go. Then f of x is left continuous. Still didn't leave myself enough room. At c. Or limit x goes to c from the right of f of x equals f of c. Then you might guess that means that f of x is right continuous at c. Right? So another way, if we look at this function here, right, this example is right continuous. Right? Because the limit as we approach 0 from the right is equal to, we'll say that's 1 and this is 3. Right? The limit as it approaches 0 from the right is 1, and so is the function value, right? That's what that filled in circle means. And the limit as f of x approaches c from the right is 3, which is not what the function is. Right? So the limit from the right exists, it's equal to the function, so it's right continuous. Right? So we can have multiple different types of continuity. Now, we have multiple different types of discontinuity as well. Right? So if 1 and 2 are true, but not 3. Right? I actually drew the picture up there. But we say there is a removable discontinuity. Right? So again, that's an idea like this. And we call it removable because if we could pick this guy up and move him up there, right, take that dot that strayed away somewhere and plug him back up in the hole, then it wouldn't be discontinuous anymore, right? We could fix that one point, just scoot it up or down a little bit, and we'd be good, right? So if both of the things exist, if the limit exists and the function exists, they're just not equal to one another, then we have a removable discontinuity because we can fix it. Right? We can remove the discontinuity. If 2 is not true, because the limit as x goes to c from the right of f of x and the limit as x approaches c from the left exist but are not equal, then we have a jump discontinuity. And this is also the picture that I drew up there for number 2, right? This guy is a jump discontinuity, right? But just to have another picture of it, that might be something like this, right? So right here is a jump discontinuity. Because the limits from the right and the left both go somewhere, they just don't go to the same place. And then the last type that we have, if either the limit as x goes to c of f of x, or the limit as x goes to c from the left of f of x, or the limit as x goes to c from the right of f of x is infinite, then we have an infinite discontinuity. Right, so we might have, as an example, this guy, right? Right, so looking at it here, this guy goes off to infinity, right? So the limit as x approaches c from the left is infinity. The limit as x approaches c on the right is just this number, whatever that happens to be. And the function value is just that number, but one of the limits associated with that point goes off to infinity. And since no function value is ever going to be infinity, we know that there can't be it can't be continuous there, and in fact we specifically call that an infinite discontinuity. Now, if something's continuous, we have some nice rules for it. So, given that f of x and g of x are continuous at c, then we have that f of x plus plus g of x and f of x times g of x and f of x divided by g of x as long as g of c is not equal to 0 are all, there's more. A constant times f of x and f inverse of x are all continuous. Right, so if you have two continuous functions, you can add them together to get a continuous function. You can multiply them to get a continuous function. You can divide them to get a continuous function as long as the denominator is not 0. You can multiply them by a constant and they're still continuous. And you can take the inverse of them and they're still continuous. Then so if we have that g of x is continuous at c and f of x is continuous at g of c, then f of g of x, right? So that composition is continuous at c. So some of the nice functions that we have that are continuous, we talked about last time. So algebraic functions, sums, quotients, and products of power functions. We also have our two basic trig functions, sine and cosine, are continuous everywhere. The others are often continuous, but there's also an infinite number of points where they're not continuous, right? So one of the things, infinite discontinuities, you have one of those wherever you have an asymptote, generally. So if you remember back to trigonometry, tangent, cotangent, cosine, and cosecant, not cosine, secant and cosecant, all have asymptotes, so they can't be continuous everywhere. But sine and cosine are very nice and continuous. Some other examples we have are logarithms, base b, and exponential functions, so a constant raised to a power with a variable in it. And any combinations of these, right? So if we have, for example, if we have the limit as x goes to 0 of 2 sine x, right? Well, 2 to the x, that's an exponential function, so that's good. Sine of x is on our list, so that's good. And we set up here that as long as they were continuous at the right places, then we can compose two functions and still be good. Right? Now, all of these functions that I've listed here are continuous everywhere. So since this is the composition of two continuous functions, that just means we can substitute. Alright, so we get 2 sine 0, which is 2 to the 0, which is 1. Alright. So I'm going to write this out a little bit more. 2 sine of x equals f of g of x, where f of x is 2 to the x, and g of x equals sine of x. Right, so depending on your pre-calculus class, you might have gone over how to decompose functions, and this is one of the places where you're not necessarily going to need to explicitly decompose them, right? This work that I did over here is entirely extra, right? That's not something that you have to do as you're going through it. But if you're comfortable with decomposing them, at least in your head, and making sure that all those pieces involved are continuous, then you can use substitution, right? So that's one of the reason that those decompositions worked out. So other than learning that if you want to do limits, you can just plug stuff in, right? Some of the more interesting problems in this section come from piecewise function. Piecewise functions. So an example of a piecewise function, let's see, let's have 2x plus 1 when x is less than -1. Let's have 1 -1, where x is between -1 and 2. And let's have 3x squared, where x is greater than 2. Keep the pattern there, where all the arrows are pointing to the left. Right, so if we were to graph this out, right, and that's one way of solving the actual problem that we want to get here, right, we would go down here, say, okay, there's -1, there's 2. So when x is less than -1, then we know it's going to look like this linear function. So it's going to be here, and it's got a positive slope, so I know it's looking something like that. This is not really to scale. When it's between -1 and 2, it's just equal to -1. So we've got this, we've got this. And then when it's greater than 2, it's going to look like a quadratic. And it's going to look like a quadratic that opens up and starts at 12. Oops. So it's going to look something like that. Right? So when we graph it and look at it this way, right, I had to pick up my pencil between these 2 points, but that's just because how I was doing the problem. If I knew what it looked like, then I could have drawn this as one big point. Right? But this guy right here pretty clearly has a jump discontinuity. Right? So this is continuous except at x equals 2. Right? Because that's where that jump discontinuity is. Now maybe I have a more complicated piecewise function, I don't want to graph it. Maybe we have a problem like what we're going to do next and we can't graph it. So we're going to first figure out how to do this one using the definition without graphing it. Right? So we're going to pretend like we didn't graph it and figure out how to do it using the definition. So one of the things that we need to keep in mind with piecewise functions is that the only time that they're possibly going to be discontinuous is when they swap over from one section to the next. Right? This is continuous, and this is continuous. So everywhere where they're just one of those pieces, it's definitely going to be continuous because it's a bunch of continuous pieces. Right? The only potential problem when you have a piecewise function made up of continuous pieces is what happens at those boundaries. Right? So first off, we're going to look at x equals -1. Right? Now our definition, if we go back up here, right, way back up here, right, is that the limit equals the function value, right? And so we need to make sure we know how to find the limit, and we need to make sure we know how to find the function value, right? So the function value is probably the easiest one, right? F of -1. Well, -1 lives in this piece here, right? Because we have the less than or equal to sign there. So we look at its function piece, and we see that that's supposed to be -1. Right? Now, how do we find the limit of the function? Right? And that's where it gets tricky because we have 2 pieces that have values that x gets close to -1. Right? This is the piece that -1 lives in. But if all we care about is x getting close to -1, then we also have to look at that piece, right? So at that point, we've got 2 different formulas for our function that we have to look at. But one of the nice things is this is always to the left of -1, and this is always to the right of -1. Right? So that means that what we can look at instead is the limit as x goes to -1 from the left, and the limit as x goes to -1 from the right. And if those are both the same thing, then we know it's going to be continuous. Right? So, if we look at it from the left, we've already said that that's looking at this piece, right? That piece is continuous, so if I'm only ever going to be in that one piece, then I can use substitution. So that's looking promising. The one from the left is equal to the thing, right? Now, if I'm going to look at the one from the right, then that tells me that if I'm always to the right of -1, but still close to it, then I'm always going to be in this second piece, and so I'm always going to be equal to -1. Right? So since all three of these are equal, we're continuous at -1. Right? Now for x equals 2, we do the same thing, right? First we look at f of 2. 2, yet again, and keep making this arrow thicker and with more lines in it. 2 lives in that piece because we have less than or equal to 2. So this is also going to be -1. Now the limit as x goes to 2 from the left, right? If we want numbers that are less than 2 but still close to it, we're again going to be in that middle piece. So we're going to be -1. If we're looking at the limit as x goes towards 2 on the right of this function, then if we're bigger than 2 but still close to 2, we're going to be living in this piece. So we have this function, and that function is continuous, so we can just do substitution. And now we've run into a problem. These two aren't the same, so the limit as x goes to 2, f of x, does not exist, and therefore we have a jump discontinuity. Right, and again, we could get all that from the picture if we wanted to draw a picture. Either one of these ways is perfectly fine, but one of the reasons I wanted to do it like this is we can do this sort of more algebraic way and check ourselves with the clearer graphical way, right? Because the graph is a lot easier. I draw the picture and it's obvious what the answer is. But so we can check ourselves, and we did in fact get the exact same thing. So, I have limited space to do this last problem, but that should be fine. So one thing we might have is, say we have a function that looks like, 2x plus c if x is less than 0, and it looks like x squared plus 1 if x is greater than or equal to 0. We want to find c so that f of x is continuous. Right? So in this case, we can't graph it, because if we don't know what c looks like, then we don't know what that picture looks like. Right? But again, we're in a situation where the individual pieces themselves are continuous. So the pieces are continuous. So f of x could only possibly be non-continuous at the change points. Right? Or change point in this case, because there's only one of them, right, at x equals 0. So what we need to do is we need to find f of 0, right? And for that one, we look at this piece, because that's where 0 is included. And we see that we get 0 squared plus 1, which is just 1. Then we look at the limit as x approaches 0 from the left of f of x. Now, if we're less than 0, but still close to it, then we're going to be in this piece, right? The definition of that piece is x is less than 0. So if we're going to be less than 0, we're looking at that piece. So we plug 0 in here, because that piece by itself is continuous, and we get c out of it. Right? And next, we want to look at approaching 0 from the right. And if we are bigger than x, but close to it, we're going to be in that second piece, because that's part of the definition of the second piece. Is the second piece is wherever x is bigger than 0. So we're definitely going to be in the second piece. And the second piece is continuous. So we can just plug in. Now, to be continuous all over, to be continuous at 0, we need all three of these numbers need to be the same. And as luck would have it, 2 of them are. So 1 is always going to be equal to 1. That's pretty easy. And that needs to be equal to c. Well, okay. We were supposed to find c, and it looks like we did. C has to be 1. If c is 1, this function is continuous. If it's not continuous, because the limit won't exist at that point. So this is doing that same sort of process as we did up here. We just don't have that picture to check ourselves with, right? Though now that we've done this, we could draw the picture, or have our calculator draw the picture and make sure that it matches up, right? So now that we've got continuity under our belt, and we can figure out any combination of continuous functions, we can find their limit by plugging in. Except when one of the pieces goes to infinity, or when a denominator goes to 0. So next section is going to be all about how do we find limits when the denominator is going to 0, or one or more of the pieces are going to infinity. So I will talk to you then.